3, 4x, wow. Hello and welcome back to Differential Equations, section 2.5, non-homogeneous equation with methods of undetermined coefficients and variation of parameters, which is, for whatever reason, not mentioned in the title, but we should give it equal time. This will take some time to cover because these are two separate methods. We are going to start with undetermined coefficients. First of all, to make sure that you remember that homogeneous equations, non-homogeneous equations, the difference is that the right-hand side is not 0, right? So, looking at the equation y double prime plus 3y prime plus 4 equals to 3x plus 2. So this is a non-homogeneous equation because of 3x plus 2 on the right-hand side. We call that forcing term, and that's generally the force that would push the system, the spring, right, the mass spring system and stuff like that. Now we recognize the left-hand side. Left-hand side we can solve by constant coefficients. We know to transform this equation into r squared plus 3r plus 4 equals 0, right? That's a characteristic equation. Then we factor it as r, help me? Quadratic formula. Yeah, okay. So negative b plus minus square root of b squared minus 4ac. Ooh, shiny. Do what? 4ac. Yeah, that's minus 9, right? Which is negative 3 plus minus, and this is negative 7, right? Did I copy that wrong? Yeah, I copied it wrong. It's a y. That has to be a y. Otherwise, you would bring it to the other side as negative 2, and the life would be different at that point. So negative 3 plus minus b squared minus 4ac, so that's 9 minus 16. And 9 minus 16 is negative 7. So we have root 7i over 2, which turns out to be negative 3 halves plus minus root 7 over 2i. Now this gives us the solution. This is the homogeneous part. So I'm going to call this yh, because this is the part of the solution. This is the part of the solution if this 3x plus 2 did not exist. So homogeneous part of the solution is going to be given with our sines and cosines, right? So we have e to the negative 3 halves x. We have to use x because you see the independent variable is x. We generally like to use t, but it's x now. So e to the negative 3 halves x, and then we have c1 cosine of root 7 over 2x plus c2 sine root 7 over 2x. Now this is the homogeneous part. We have to find the particular part now. And for particular part, we are going to use method of undetermined coefficients. So now we are still working the same problem. Method of undetermined coefficients to get rest of the solution. Now that part we call particular part of the solution, and that will be added to yh, and together they create the solution for the general solution for the... I don't like that this part is called particular, and then you add it to the y homogeneous to get the general solution, and then if you have initial conditions, you get particular solution again, which is, but such is life. Way too many people work on this. So let's see the method. So the method is going to take the forcing term and get derivatives, first and a second derivative. So we are going to start with just take derivatives of 3x plus 2. So those derivatives would be, well, this is f. F of x, right? That's the notation. 3x plus 2. So f prime of x is going to be 3, and f double prime of x is going to be 0. The amount of derivatives you're taking is going to match the order of the differential equation, because now you are going to plug this in. Now, before you do that, you observe the, well, actually you can go over here the 3rd degree and 4th degree and so on. You can go as many of these as you want, because you are looking for the pattern. And if you observe this, the pattern is ax plus b. All of these infinitely many derivatives you are taking are going to fall into this pattern. So we are creating yp as ax plus b, and there are your undetermined coefficients, a and b. And we need to figure those out. The way you figure those out is you plug this into differential equation. I'm going to write that in red because that is your procedure. Plug this and its derivatives into DifEq, differential equation. So yp prime is a and yp double prime is 0. Now we plug this in. Original equation was y double prime. Well, y double prime is 0 plus 3 times y prime is a plus 4 ax plus b needs to be equal to 3x plus 2. This is a little bit similar to partial fraction decomposition, if you remember, except this is more convoluted because you take 15,000 derivatives and plug stuff in. In b, in parentheses, yes. So if you recall, your original equation was y double prime plus 3y prime plus 4y, right? So for y double prime, you plug x or ax plus b, and then you go from there. Now you have the equation, get a and b. So what do we have? We have 3a plus 4a plus 4b is equal to 3x plus 2. Same thing like in your partial fraction decomposition. What happened to my x? There we go. So now we have 4ax is equal to 3x, and we have 3a plus 4b is equal to 2. Because you are matching the coefficients of x with coefficient of x, and then the constant terms with a constant. Same thing that you did for your partial fraction decomposition, section 7.5 in Calculus 2. Same thing. From the first one, we are going to see that x's obviously cancel. So 4a, 3, so a is 3/4. And then we plug that into second equation here. So 3 times 3/4 plus 4b equals to 2. So that's 9/4. plus 4b equals to 2. 9 quarters, so you subtract that, you get negative 1/4, I hope. And then times, divide by 4 both sides, so times 1/4. B is negative 1/16, I hope. So particular part, yp, is going to be 3/4 x minus 1/16. So what is the general solution now? General solution, y of x, is going to be yh plus yp. Now, your yh is good old e to the something, 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 and then something with cosines. All right, negative 3/2 x c1 cosine root 7/2x plus c2 sine root 7/2x, and then we have plus 3/4 x minus 1/16. So next time you're tutoring someone in algebra and they say this problem is very long, flip through your notes. Now this is obviously one of the very short problems because we had a forcing term of 3x plus 2. Imagine the forcing term of e to the 2x cosine 5x. Yeah, you'll need 2 notebooks for that one. It's coming up. So let me review one more time the method of undetermined coefficients. These chairs are actually freakishly comfy. They don't look comfortable at all, right? They don't look comfortable, but we'll see if anyone can fall asleep in one of these chairs. That will be ultimate test. All right. So the shortest problem took a page, right? Guys, let's review all of this. We're starting with the differential equation. We are understanding that there are 2 parts to this. There is a part on the left which we can separate and call and have it as a homogeneous part, which we solve with characteristic equation and grind through whatever we get. Either distinct real roots, repeated real roots, or complex pairs for sines and cosines. So we grind through and that part, that particular part, or this stuff, is the constant coefficients from 2.3. So that's 2.3, and then when you're done with 2.3, you have your homogeneous part of the solution. You are ready to start method of undetermined coefficients to get the rest of the solution. The rest of the solution exists because this is a non-homogeneous equation. It has this what we call forcing term, and this guy is that f of x, which we have seen when we defined differential equations of the higher order. We said equal to f of x, which is a forcing term. So now we are going to see that that forcing term is 3x plus 2. So what you do is you take infinitely many derivatives of that. Infinitely many derivatives. And infinitely many derivatives will tell you the overall form. You have to find the form that fits all of those infinitely many derivatives. There is a form that you can pack all of them into. Yeah. No, it's not going to be. We'll see. So you get this. And then when you have that form, you create particular solution using that form, and then you take the number of derivatives that matches your equation, the order of your equation. Because we have the second order derivative, second order equation, we take 2 derivatives. Plug that in the original differential equation, keep the forcing term in this time around, Solve this using the same methods you learned in partial fraction decomposition. Get those A, B, C, how many you have. And finally, at the end, add homogeneous and particular solution together to get the general solution for this equation. Then, if you have the initial conditions, you will use those initial conditions to figure out C1 and C2. And good luck with that, right? Because you have to do that product rule over there and a bunch of other calculations. Let's take a look. I'm going to jump into homework exercises because I am well aware that you guys know all the letters and numbers to read what's solved in a book. So I'm just going to solve something that is not solved in a book. We have more examples. Well, such is life. The only e to the x that I see that has nothing diabolical attached to it is problem number 1. Oh, and problem number 20. Yeah, number 1 it is. Or 20. 1 or 20? 20. I knew it. That's called power of suggestion. This is problem number 20 in your textbook. Left-hand side is r cubed minus 1 equals to 0. To factor this, we know we can take r minus 1 as a factor, right? So we have r equals 1 solution, which gives us r minus 1 as a factor, and that one divides into r cubed plus 0 r squared plus 0 r minus 1. We will use synthetic division, so 1 coefficients are 1, 0, 0, negative 1. So drop 1 down, multiply, add, and then multiply, add. So we are obtaining the equation r squared plus r plus 1 equal to 0. And with this one, we unleash quadratic again. So negative 1 plus minus square root of 1 minus 4 divided by 2. So that's negative 1 plus minus square root of 3i over 2. And we are getting the solutions for this guy. R equals negative 1/2 plus minus root 3 over 2i. So we are at the homogeneous solution, which is e to the R1 first. So C1 e to the x plus e to the negative 1/2 x, open parenthesis, C2 cosine root 3 over 2 plus C2 sine root 3 over 2. Oh, I forgot the x over here. Oops. So this is our homogeneous, and what you see on the screen right now is just a standard 2.3. We haven't done anything new on this, except maybe review this a little bit annoying factoring that we had to employ. Now is the time for undetermined coefficients to take care of the rest of the solution. We have to find a particular part. So, yes?
After the C1 e to the x plus e to the 1/2 x.
This is supposed to say C3 over here. C1, C2, C3. We know that we had the third order differential equation. We better have C1, C2, C3, right? We better have three constants. Great. So we are done with this part, right? Now we are going to start with undetermined coefficients. I am going to get the, well, first I'm going to get my phone plugged in. What are we having? Right. So now we are going to, I'm going to again, method of undetermined starts. So I'm going to announce where we start with the undetermined coefficients. So we start here. I extract f of x, which is e to the x plus 7. And I take infinitely many derivatives. Now, what it turns out is that infinitely many derivatives all settle on e to the x. Now, what is the theme for this? What is the YP looking at all of this? E to the x plus a. Very good. Why is it plus a? Because it used to be plus 7, and then it's plus 0 forever. So there is a change on this part. Coefficient of e is always 1, right? Now you can see this changed a little bit. If you had e to the 3x, the next derivative is 3e to the 3x. The next derivative is 9e to the 3x. And then 27e to the 3x. So this form would be ae to the 3x because coefficient in front is changing. Over there we have a plus 7 and then plus 0, plus 0, plus 0. So 7 changed into a 0, but the coefficient of e stayed 1 all the time. So that one stays 1 all the time. So you can, that one was 1 here and here and here. Everywhere was 1. So you don't have to put the coefficient in front of e to the x. But if the problem is different, then you see that the coefficient in front changes all the time. Then you have to put that a in front. So whatever changes as a coefficient, you have to change, you have to capture that with your variables. So now you have this. And then we take two derivatives of this, which is e to the x and another e to the x, to plug them into original differential equation. No, 3 derivatives, right? 3 derivatives. The number of derivatives taken here has to match the order of the equation. And now we plug in. So original equation was y triple prime, so that's just e to the x, minus y, well that's e to the x plus a, minus a, equal e to the x plus 7. I don't like this. Because my e to the x is cancelled. Yes, there is a problem. Because you see that these guys, oh, and a is negative, yeah. So a is negative e to x minus 7. There we go. Wait, it doesn't cancel. Wait. Let me plug in one more time. Hold on. So original equation is y triple prime minus y is equal e to the x plus 7. This is e to the x minus, this is e to the x minus a equals, what happened? Plus a, yes. So now, these guys cancel. We have negative a equals e to the x plus 7. A equals negative e to the x minus 7. And then plug that into yp, which is e to the x plus a. They cancel, and you get yp is negative 7. And there you go. So now y of x is equal to yh plus yp. Y of x is c1 e to the x plus e to the negative 1/2 x c2 cosine root 3 over 2 x plus c3 sine root 3 over 2x minus 7.
What is that? That's kind of weird though. Like, what is the y, the minus 7 add to the equation at all? Oh, actually, no, wait, no, it's not.
Because that minus 7 will play a role, right?
Yeah.
It is, but it works. Ready for the spicier examples?
That was pretty spicy.
Yes. You're talking about something in here, right? Oh, this one. Yp is defined as e to the x plus a. And a is minus. So when I plug that, so this is yp is e to the x plus a. And a is this, so that's how you get these, the second two. And then they cancel. All right, try to enjoy this one on your own. And then we'll take a look at it together. We'll do 2 more examples of undetermined coefficients, maybe 3, and then we'll move to variational parameters if we have time. Depends on how fast you move. Guys, this is problem number 3. You're going to love it. Y double prime minus y minus 6y is equal to 2 sine 3x. Yes.
How do you know that I've got the R equals 3R equals -2? So we put the -2 for the 1 and then 3 for the C2.
Or it doesn't matter.
It doesn't matter?
No, because addition is commutative.
Because what?
Addition is commutative, so we can put in any order.
Oh, you can't.
George, would you please do me a huge favor? Can you get my weapon? My weapon? Well, that depends on the trio over there behind you.
I got that far. Now you get to the first derivative. You sine 3x is cosine 3/3.
So now I'm going to take a whole bunch of derivatives here.
What rule is that right there? Chain rule.
So chain rule will keep kicking the 3 in front, and sine goes to cosine, cosine goes to negative sine, and so on. So it looks like we always have sine 3x, cosine 3x with whatever coefficients. All of these can be packaged into a sine 3x plus b cosine 3x. All of them can be packaged into this.
So, basically using the pattern?
Yes. You look at the pattern, and the pattern is, it will always oscillate between sine and cosine. 3x always stays the same. So coefficients in front change. Yes?
This looks very similar to the imaginary pair. With C1, actually, no, you're right. With the C1 sine of dx plus C2 cosine dx.
Yes, because sine and cosines are both defined through imaginary.
So, in the original problem, it's kind of set up to become like this. Because the forcing term here is sine of 3x, or 2 sine 3x.
Mm-hmm.
So, it would have a, you see what I'm saying?
You're saying that this looks the same as the homogeneous part from characteristic equation that had 3 on a complex. Yeah. Because you can have a wave-like behavior in the input, right? You think of pushing a child on a swing, right? You periodically apply the force. You have the, what do you call it? Or 10. You have a period when you're applying the force, which is the positive hop, and then you have one that you don't do anything, and so on.
Yeah.
All right, so now we have our yp. So now we need yp prime, which is the derivative. That's going to be 3a cosine 3x minus 3b sine 3x. And y double prime p, we need 2 derivatives, because our equation. It's going to be negative 9a sine 3x minus 9b cosine 3x. How we took these derivatives. The next order of business is to plug this into differential equation. We are working on problem number 3. Thank you. So y double prime, which is negative 9a sine 3x minus 9b cosine 3x, minus y prime, So minus 3a cosine 3x plus 3b sine 3x minus 6 times the first one. So 6a sine 3x minus 6b cosine 3x equals finally 2 sine 3x. There we go. This is all one equation. You are going to collect like terms. That's all of the sines on the pile and all of the cosines on the pile. Where are my sines? This is the sine, this is the sine, and this is the sine. So what do I have for sines? Minus 9a, minus 6a is minus 15a, and then I have plus 3b. All of that times sine 3x plus blah for cosine 3x equals to 2 sine 3x. Now what's happening for the cosine? I have negative b minus 6b is negative 15b, and I have what for a? Negative 3a. If I collect all cosines on the pile. So this is our red, and then the blue, 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 blue. Great. That stays there. Now we equal coefficient of sine x with the coefficient of sine x. We are getting negative 15a plus 3b equals to 2. And finally negative 3a minus 15b equals to 0. Two equations, two unknown. I'm going to use method of substitution. If I divide bottom equation by negative 3, I get a plus 5b equals to 0. A is negative 5b. Plug in. Solve this any way you want. Matrix, I don't know, beans. Use Ouija to call on spirits and then solve this for you. I don't care. Just get it. That might be a little bit excessive, but you might know how to do it. I don't know. Negative 5 times this is negative 2575 plus 3b equals to 2. So that's 78b equals to 2. B equals to 1 over, is 39 good enough? No one cares? Fine. And then A is equal to negative 5 over 39. Uh-oh. Should we take it outside?
Oh, I'm saying for B, I got negative 1 over 36. Not for A.
Well, I got 1 over 39, so what now? So they're great. We have 4 people involved, and we all have different answers. So thou shall use what? Wolfram Alpha to check on our 7th grade math? Excellent. I'm sorry? I just got confirmation on my answer, so. The Matrix said so. Neo has spoken. By the way, Neo is not the one. You know that, right? He's the boss, yeah, but he's not the one. Think about it. It was the only program that could replicate himself. That was one of the... Yep.
Oh, wait, are we talking about Matrix? Yeah, Matrix. Oh, that's fine.
No, when you really pay attention to the whole thing, you see that he's the only one.
Yeah, but like, also, like,
Artificial intelligence.
so much like oh yeah. Special?
Mr. President, do we have a consensus on 139?
I don't want to talk about it.
You don't want to talk about it? Excellent. Because I was about to spend $5,000 right there. All right. So our undetermined coefficients became determined coefficients. And we are looking at yp, which is negative 5 over 39 sine 3x plus 1 over 39 cosine 3x. Our solution, general solution, is addition of the homogeneous part and the particular part. So y of x is equal to c1 e to the negative 2x plus c2 e to the 3x minus 5 over 39 sine 3x plus 1 over 39 cosine 3x. Please keep in mind, guys, that someone came up with this stuff. Probably Bernoulli's. Probably Bernoulli's. Of course not. I don't think that people can actually do any of this. They're too distracted by nonsense. By hanging out and things. Yeah. The gold era is over. You do? All right. I'll put arrows on this one because it looks nicer. All right. Since you are so into this stuff, let's pick another one that you are going to love to hate. Ooh. What happened? Is that okay with you? All right. Ready? And action. Y to the fourth derivative of y minus, yes, because I'm coming from the pre-calculus class.
Why don't they like change the things so that it's easier to read?
Because what would you be discussing then? All right, so are you all good with this? You understand this part? Now, after this, we have that y of 0 is the same as y prime of 0 is agin, and y double prime of 0 is the y triple prime of 0 is negative 1.
Oh, they're just I was like, what happened though?
Differential equation collapse happening. Oh, by the way, you got everything for the drone?
Yeah.
Good. We'll schedule another. Oh, yes.
And also email I sent.
Email that you sent me today?
Yeah, send an email around 3:40. Maybe 3:36 a.m. Yeah.
Sent me an email today.
They have like 5 different emails?
Aha! There's an email from you from 2:38.
2:38.
Yes, 2:38. Oh, no one will show up.
Well, at least one person though.
Exactly. If you go for it. You said you sent 5. That's it.
What?
You said you sent 5 emails. That's it.
I said one. No, one email.
Oh, okay. Very good.
No, you factor this. You factor out an r squared. So you get you have r4 times 4 squared minus 4 squared, and you factor in r squared. You get r squared times r squared times 4. No, r squared is 0 multiplied by 0. 4 minus 4 squared is 0.
Yes.
There's no like a difference between when we find A or what we think is A, where do we go from there?
Then you find B.
So this is where I get there.
But see how it's a prime, so this is different constant than this one. There's different constant than this one, so this has to be ax squared plus bx plus c. And then you grind from there. All right. Now, would you do this on the board quickly, please?
Yeah, well, I'm just worried
Yeah. So we factor out r squared. We are left with r squared minus 4. That factors further into r minus 2r plus 2. And we have r equals 0, multiplicity 2, r equals 2, and r equals negative 2. So we see that we have a repeated solution, right? If you have a repeated solution, you have to make sure you're multiplying it with x. So y homogeneous is equal to r equal to 0 is c1 e to the 0, so just c1, plus, and then c2 e to the c2x e to the 0, but e to the 0 is 1, plus c3 e 2x plus c4 e negative 2x. 1, 2, 3, 4 in our superposition, and it was the 4th degree, so we're good there. Method of undetermined coefficients starts. Mook. Our f of x is x squared. The f prime of x is 2x. The f double prime of x is 2. The f triple prime is 0, and all others are 0. This triggers, we don't have to go with ax squared, right? We can just write x squared. Can we do 2x too? Yeah. I believe you can just write x squared plus 2x plus, and there's only one coefficient that you have to figure out. Because this one doesn't change. It's always x squared. There's no...
But it doesn't have a 2x. So shouldn't there be ax squared plus 2bx plus c?
Why would it 2bx when there are no other x?
But there's not 2x in the first equation or the third equation.
You already took a derivative. It's another derivative.
So?
What's the question? What is the answer? Why is it not?
Okay, let's write, if it's going to make it. So yp is 2ax plus b. Y double prime p is 2a. Y triple prime p is 0. And y to the 4th is 0. Plug this in the differential equation. We are working on problem 36. So 0 minus 4 times 2a is equal to x squared. Right? 0 for the 4th minus 4 times y double prime is equal to x squared. Good. So now you compare this, we have negative 8a equal to x squared. So from here we see that no, a is 0, so this is why x squared 2x2 0. All others are zeros forever. And you see the method, you see how you get this a equal to x squared, but there is nothing there. So this is the reason why I wanted to use this and just a constant at the end. You can call it a. The derivative of this is 2x
Once you solve for that one,
plus 1.
you're not, once you get to that, the second derivative, there is no a to actually solve.
Exactly.
So
So this is 2, and then each one is 0. So now, when you plug that in, you have 4 times, I lost my problem now, 36. So it's 4 times 2.
you can solve for me.
Wait, what's
A has
Isn't that supposed to be 2x?
something is wrong.
well, the pattern doesn't.
Wasn't the middle term supposed to be 2x?
2x right here.
No, for the YFD.
Oh yeah, okay, yeah. So that goes, yeah, and then that one and make it. But again, it doesn't change.
Oh yeah, that's 2x. Yeah, it doesn't change anything in terms of the...
The pattern of changing the actual form of the statement, the x squared, that varies. There's an x squared term in everything, but it varies. So like the first one, a is equal to 1, and then everything down there
is 0, yeah. But there's something... Oh...
No, come on, how far up is the dude?
No. Look at this. I'm trying to figure what is going on. Look, guys. Look. See? They're repeated. We have to bump x's up for these guys. You know when you have repeated solutions that you have to multiply by x, right?
Yeah. Yes.
So I did that in the YH, but then they repeated again in YP. You are not allowed to have them in YP.
How do you know if they repeated one?
Because I have eyes and I see it right here and right here. So we bump them up. Equals to x squared. Because when you take a look at the derivatives here, right? You are going to have ax squared plus bx plus c. The solution already contains c1 plus c2x, which repeats right there. Fair?
No.
So you want to bump bx, which is repeated, you want to bump it into x squared, but x squared already exists. So where you bumped it? X cubed. Now you want to bump c into cx, that already exists. You want to bump into cx squared, you can't, it still exists. You bump it, so eventually it's right there.
So it's ax squared plus 3x cubed.
Yeah, are you like that because you didn't multiply by x? The two things you didn't divide.
What happened?
How
how are you able to change the function yp?
Because this is the form of your solution at the end, and the solution has to be linearly independent.
Okay. I see that. So as long as A, B, and C are different from each other, then like they're not scalar multiples of each other, then you're fine.
Yeah. Now I'm trying to think if this was the way to fix it, or we have to multiply. Well, if this doesn't work out, I think then we have to use the different function. Let me check. So this is 2ax plus 3bx squared plus 4cx to the 3, and then 2a plus 6bx plus 12cx squared plus 0 plus 6b plus 24c x plus, so now 6b, that's dead, and we just have 24c. When we plug this in the original equation, I need the fourth one. Fourth one is 24c minus the 4 times the second, which is 4 times 2a plus 6bx plus 12cx squared, all of this equal x squared. There we go. It's obvious. Minus 24b. Don't you love when a book writes it's trivial to show, and then they write the line, and then you can't figure out for like 4 hours what was the transformation we used? Yeah, proof is trivial, and that's called proof by intimidation. Actually, when the book writes that, it's known as proof by intimidation.
See that website that lists all the proofs, and there's one like proof by superiority? It's like,
No. Can you find that? I'm interested. What's the proof by superiority? I never heard of that. All right, so we found now this is the constant term, this is the x term, this is the x squared term, which matches this one. The rest are equal to 0. So 24c minus 8a is equal to 0. Negative 24b is equal to 0. And negative 48c is equal to 1. C is equal to negative 1 over 48. And then that's plugged in here. B is immediately 0. So when we plug this one in there, we get 24 times negative 1 over 48 equals 8a. These guys cancel, negative 1/2 equals 8a. A equals negative 1 over 16. Bueno. So A, we have A, B, and C. Yes. So negative 16x squared. So yp is negative 16, negative 1 over 16x squared. And then where is B? So that dies. And then where is C? B. Yeah, B for x cubed. And then because B is 0. Maybe I should, let me just circle them in green. Well, I can't find them over here. So negative 1 over 16x. I'm plugging everything in the yp over here. Yeah. Oh, so I have A, B, C. I found them. So B was 0, so that term dies. A is negative 1 over 16, and C, x to the 4th. So negative 1 over 48, x to the 4th. There's the yp. So now finally the total solution is C1 plus C2x. Scroll 3 pages up. C3E2x. C3E2x plus C4E negative 2x minus 1 over 16 x squared minus 1 over 48 x to the 4th. Holy nightmare. I can. Now, we have to solve initial condition. Where up? Said scroll up. Where? Is everyone good with this so far? So all we need to find is y prime, y double prime, y triple prime. So C2 plus 2C3 E2x minus 2C4 E negative 2x minus cancel by 2, 1 over 8x, and then 4 minus 1 over 12x cubed. The second derivative is that dies 4C3E2x plus 4C4E negative 2x minus 1 over 8, and then this part over here, 3 cancels, negative 1/4 x squared. And the final derivative, the third derivative, is equal to 8C3E2x minus 8C4E minus 2x. That dies minus 1/2 x. Cool, right? Don't worry, you're getting 4x4 matrix to solve here. What are we having? So now, so starting with first, we have y of 0 is 1. So 1 is equal to C1. This one is 0, so it dies. This is plus C3 plus C4. 0, 0, they all die. Great. Next one, also 1. C2 survives, plus 2C3. And then minus 2C4. This dies, this dies. Good. And then we have a negative 1 for the second derivative. 4C3 plus 4C4 minus 1 over 8. That actually survives. And then x squared dies. And then a negative 1 on the last one. 8C3 minus 8C4, and then that one dies. Great. So now we create matrix, augmented matrix, and we use RREF, row reduced echelon form, on the calculator to solve this quickly. So the first one is 1 on C1, 0 on C2, 1 on C3, 1 on C4, and in augmented part over here, 1 as the answer. Then we have 0 on C1, 1 on C2, 2 on C3, negative 2 on C4, and 1 as the answer. 0, 0, 4, 4. This 1 over 8 has to go, so negative 7/8. Right? Because you have to combine this with negative 1. So negative 1 plus 1 over 8 is negative 7/8. And then finally we have a 0, 0. Yeah, do this by hand. Is that 8, negative 8, negative 1? I can hear calculator clicks already.
Well, you could do it by hand. They've already started it for you. So.
Yeah, you can do it here. Times 2, no, times 8 to kill the fraction. Times 8, and then times 4. So you have 32, 32, negative 7, 32, negative 32, and negative 4. So when you add them, this becomes 64 equals to for C3 is equal to negative 11.
Negative 3. Subtract. Wait. You're subtracting the C3s.
I'm adding
Oh, okay.
C4s into 0. What was the verdict? What's C1? C1 is, hold on. C1 is 39 over 32. C2 is
5 over 4.
5 quarters. C3 is what's that as a fraction?
11 divided by 64.
11/64. And C4?
3 over 64.
3 over 64. Great. So now we can write the particular solution for this. Y of x 39 over 32 plus 5 quarters x plus 11 over 64. So we are halfway done with this lecture. We have variational parameters. That's next class. And then we'll do the review and then exam. Right?
That's it, or you still got to wait?
No, it's 48, right? 1 over 48? Yep. There it is. How's it like? Good. No more running around. Right?